Okay, so let me transfer this to the slide presentation. So here should be the first slide, the title. The focus is going to be on the southern hemisphere stratosphere and the southern hemisphere polar vortex that is very strong in the during the winter time and spring, as we will review in a second. I'm really an aficionado, so to speak, in this subject. This is a subject for where mathematics, applied mathematics, has a very, very strong component. So sometimes my language is smooth. I hope that it was in the lectures of yesterday and before yesterday. So these are the references. There are 3 papers that have been published. One in the climate dynamics, the first one, and the other 2 in the Journal of Atmospheric Sciences. The last one is in press, is available on early release. The first author of these 3 papers is Álvaro de la Cámara. Álvaro is a student who got his PhD at the University Complutense in Madrid, but he did most of his work here at UCLA. And when the time came for his degree, the people in Paris stole me. So he is now in Paris. The third author in the first paper is Caio Ide, and in the second paper and the third paper, you can see a name over there, Ana Maria A.M. Mancho. And Mancho is a mathematician at ICMAT in Madrid, which I have visited, and I have enjoyed these visits very much. Okay, Caio Ide and Ana Maria Mancho are from Wiggins group, the Wiggins school, so that they started in Caltech. So those of you who are familiar with this type of a school will see will follow that type of approach. Okay, so a few things for the uninitiated in the jargon is that when we refer to the wind, we are usually talking about the motion of air in the horizontal direction. And then we have components of the wind vector from west to east and from south. From west to east, we call it the zonal component. Okay, the zonal wind component we say is positive when the wind goes from west to east. Whereas the component that goes from south to north, we call it meridional component, and it is positive when it goes from south to north. So that's the description of these two components. Okay, the vertical component in the atmosphere is small usually when the motions we are considering are of very large scale, say when the horizontal size of the vortices that we are talking about is of the order of 2,000 kilometers or so, then this horizontal wind component is more important than the vertical wind component. But that's a very rough statement. Okay, the following plot is a little bit complex and tries to give you a feeling of the seasonal evolution of this west to east component of the wind. How does it change in season, and how does it change as a function of latitude and height? So all of this is coming in this plot. Okay? So what we have here is for the different seasons, and the label now for the different seasons is in Spanish. So DEF is diciembre, enero, y febrero, and so on and so forth. But you can see this is the top left, therefore, is the summer season in the southern hemisphere. Okay, when we, as well as our Argentinian neighbors, go to the beach. And the quantity plotted is a magnitude, is a zonal wind component, so the component from west to east, as I said. And whereas the positive values are in red and the negative values are in blue, and meaning that the positive values are from west to east, as I said. So the stratosphere is indicated by the upper part of the plot, okay, above, say, something like 20 kilometers, and the top of this plot is at about 50 kilometers, okay, 50 kilometers. And if you look at the horizontal, the abscissa is the latitude. So each one of these plots goes from the South Pole to the North Pole, okay, from the South Pole to the North Pole. So the left part of the plots represents the southern hemisphere, and the right part represents the northern hemisphere. Okay, so the big feature of the stratosphere is that during the winter season, and also in the early spring season, the flow from west to east is dominant, and it is from east to west. Okay, it goes from east to west. Whereas in the winter time, the flow is mostly from west to east. So this is a really spectacular change, geophysical change in this enormous vortex that goes around the pole. Change the direction from the winter time to the summertime, and the same thing happens, of course, year after year, with variations that are relatively weak in the southern hemisphere. The southern hemisphere is a very nice and smooth southern hemisphere in a certain sense, because the topography is not that large, so boundary conditions are more in the sphere. So this vortex is more centered, so to speak, at the pole. Okay, so like a gigantic tornado going from in one direction in one season, in the summer season, to the opposite direction in the winter season. And in between, of course, there is a lot of mix-up. As when one is stirring a cup of coffee in one direction, and then it changes and steers the cup of coffee to the other direction, there is mixing. Well, the reason, of course, for all of these changes have to do with the way the sun, the solar radiation forces the motions. There's a big difference, though, between the western part and the eastern part. So I made a cartoon. That hopefully is a little bit amusing to you. In this cartoon, what we are doing is we are looking at the 30 kilometers high in the stratosphere. And I thought, well, how can I kind of represent this for a person that lives in Los Angeles? Well, in Los Angeles is very characterized by freeways. So let's say that we have these two friends over there. You know, one of the friends has a red bottom, so we can see this friend. This is the fun-loving friend. The other guy is more circumspect. And so they are in Antarctica. In Antarctica, they are quite bored because when the winter time and in summertime, this vortex, the San Diego freeway, is so strong, the traffic, that they cannot go through. Okay, they cannot go through. So they stay there the entire season. When the summer comes, the late spring and the summer comes, then the flow changes direction. And it was difficult to me. I'm not good enough to plot the change in intensity, but it changes direction, and it also becomes weaker. Okay, it becomes weaker there we go. It becomes weaker. So actually, the fun-loving guy escapes and can escape from this confinement. And you can see this on the upper left, enjoying with their friends some of these beautiful nightclubs in Buenos Aires. Okay, so this has been the usual description of the situation in the stratosphere, and with the winter being very isolated air, and most of the air is ocean is horizontal. Okay, so describing what happens at this height is a good approximation. Okay, now how this came about? This came about because of the problem of the ozone hole. And I myself worked quite a bit on the southern hemisphere stratosphere when the ozone hole was discovered, and realized to my dismay that in the younger generations of students that I teach here at UCLA, some of them they haven't even heard about the problem of the ozone hole, being the problem mostly solved, and the reason for the destruction of the chemistry of the ozone is basically discovered, and the measures have been taken to modify to remedy the problem. But there are many questions that have remained, the dynamical questions have remained. So this is the situation. That's an artistic view, say, of this, the Earth, the South Pole. You see where the arrow, the blue arrow is pointing upwards. Antarctica is really high. It's a high plateau. So here we have the vortex rotating in this type of view in the clockwise sense. Okay, and inside the vortex, the air is pretty much isolated horizontally. Okay. Now it's fed vertically, but the vertical motions are very weak. Okay, so the big way to bring the air from lower latitudes to above Antarctica doesn't happen because of this vortex isolation. When the inside of the vortex, it really becomes very cold. Now, where is the ozone-rich air now? The factory for the ozone is outside the vortex, because to make ozone, you need two elements. You need oxygen and you need sun. Okay, the sun breaks the molecule of oxygen, and that is O2, two atoms of oxygen, and then if two become one and one, and this one goes around and gets hooked to an oxygen with O2, and then forms O3. So you need the sun. So during the winter time, there is no sun at the pole. And during the winter sun, everything is cold, dark, and dreary, and all of that. But in the springtime, the sun comes. And now the sun comes and start messing up things. In particular, getting the pollution also broken down. And when the pollution gets broken down, some of the bad guys, like chlorine and bromine, they wake up. And they wake up and start destroying the ozone. So that's a theory, and it has been, after so many years, it has been kind of accepted. The important thing is that, believe it or not, this story repeats itself every southern spring as the sunlight returns to the pole, which means that there is no destruction of ozone in the summer. In the summer, actually, the vortex starts going the other direction, and particles with ozone-rich air can come to the pole, right? So the ozone hole disappears in summer. And so there is no ozone hole in the summer. There is ozone hole comes the next spring and the next spring. And there was one of the big questions that people had at the beginning. Why only in spring? Of course, the question was why only mostly above Antarctica? Why not over the Arctic? Well, we know that most of the pollution is produced in the northern hemisphere. Okay, so this is one of the recent plots. March 2011. Okay, pretty late actually. There was an unprecedented ozone loss over the Arctic. You have also distraction, of ozone over the Arctic, and that has that shape, and that shape roughly corresponds to the similar vortex that is in the northern hemisphere. Okay, so after some time, the problem became so serious that even in the northern hemisphere, we started feeling the destruction of ozone. However, this also is distracted only in places where the temperature becomes very, very, very cold. And that's much more common over Antarctica than over the Arctic. So the nature has conspired to make the ozone hole over the Antarctic and not so much over the Arctic. Well, the point here has been the fascination with this vortex and how this vortex is isolated in terms of Lagrangian motion, how the parcels stay outside or stay inside and then do not move across. Okay? So from lecture 1, I have these two equations. There are so-called conservation properties. The time derivative with respect to time, the derivative with respect to time means that we are following the motion of a parcel of air. Okay, so if we neglect heating, we neglect friction, then there's a quantity called potential temperature that, for all that matter, really you can think about that as very close to temperature. It's not exactly like that, but it's not so bad, and that is conserved. So a parcel will move around, and we'll always keep that the value of that quantity theta. The second one is more complicated. It has to do with the vorticity. Okay, so this vorticity is the way in which air goes around in vortices, and it has a component that includes the effect of the rotation of the Earth. So that component is called Ertol's potential vorticity. Ertol's is a name of a person. In the future, we just may say potential vorticity. Okay, so a parcel will keep these two properties. We do not have another property for a parcel. If it were conserved, then a parcel will, in a three-dimensional flow, will be characterized by three properties, and then we will be working with these coordinate system. That would be great. But we do have two properties that if there is no friction and there is no heating or appreciable heating, then the parcels these two properties are approximately conserved. And in the stratosphere, it turns out that parcels satisfy that property for about 15 days. So if we are looking at things that happen in periods of 15 days, and we can really look at these two properties and say, okay, they are helping us to describe the motion of air parcels. In the ocean, I imagine that Oscar Fuentes has talked about these things with other variables, perhaps with potential temperature too. Okay, so some basic. So let's look at these fields. Okay, now this is the real world. On the right-hand side of this plot, I mean the only figure in this plot that you are seeing so far, we have a map, and perhaps you can see South America here on the upper left. Okay, at the tip of South Africa over here, and Australia over here, and Antarctica in the middle. Okay, and this is a map. The contours show potential vorticity. So that quantity that is conserved. And the surface that we are plotting is a surface where this other potential temperature is constant. That means that parcels that were on that surface are constrained to stay on that surface because the potential temperature is conserved, okay, in 15 days or so. Okay? So a parcel on that surface will remain on that surface. Also, in the contours, a parcel on one of these contours will move around, but will remain in that contour. Will remain in that contour because potential vorticity is conserved. So this map has been pretty useful And now you can see it's a very smooth map. And it's a very smooth map, even though potential vorticity has some higher order derivatives, because data in the stratosphere are not that, we don't have such fine structures of data in the stratosphere, so they look very smooth. And the impression that we are getting now is that we have a location where there are very tight gradients of these contours separating a part in the outside from another part of the inside. And these very tight gradients of the potential vorticity is the equivalent to the San Diego freeway that I was talking about. Okay, so the parcels wouldn't be going through these regions of the strong gradient. And to kind of reinforce this impression, I can show you in the left-hand side the map of ozone, again from data for that particular day, 15 October 2000, corresponding to the same day that we plot other dynamic quantities on the right. And the blue is the low ozone, and the red is the high ozone. So you see how the high ozone through these lines, this boundary of the vortex, and the isolated inside. Okay, so inside is isolated. It's very, very cold. The and the chemistry will start. Okay. Now the vortex is not perfectly circular. It's not perfect. That propagate from the troposphere, for example, and associated, say, with the topography of the continents. Okay, nothing is totally symmetric, so this perturbation propagate up, and the vortex does not have a perfect circular shape. And these very large scale waves, we are going to be called them just Rossby wave. Rossby is a very important name in our field in dynamic meteorology. Okay, now if we look at these plots, this is another one for 1 September 1996. It looks very smooth. So if we really believe these plots, then there is never a change of air between the inside and the inside of the vortex. Okay, but there is. I mean, there is transport. There is transport, and we know that even by considerations of a budget of the ozone in the vortex, we do have to consider leaks. Looks through this vortex, there have to be leaks, and we do not see the leaks with the observational data from operational centers because the resolution is so low. But we can look a little bit more in detail to some other days. I don't know. Say, for example, here we have 15 October 2005 and 30 October 2005, and we see something quite remarkable. These structures around these tide gradients now, they are giving place to a filament. Okay, these are these filaments that are separated. One can even imagine a process like a vortex over here that is peeling away a part of the air that was in the wall of that vortex. Okay, and here is another one. Mind you that everything is rotating very fast. So from the left to the right in these 15 days, this vortex has been around, in the cyclonic sense, or in the clockwise sense, quite a bit. Okay, and now we are getting the feeling that if this is true, then a parcel that was in this filament, okay, is going to stay in the filament. So this parcel now is getting really, to the middle of the Pacific Ocean. So at least the parcels that are close to the vortex on the outside are getting away. From now, to explore these problems, years ago, the French initiated a big project And it turns out that this project was divided in two field campaigns: VORCOR for Vortex Core, and Concordiaci for the French station from where this campaign was going to be held. And what they did is they developed these gigantic balloons. This is one of the balloons going up. The balloon is not spherical yet. It will become spherical as it goes into a very low pressure area. The references for all of these activities are in the papers that I mentioned at the beginning. Okay, or some of them are over there. Albert Herzog at École Polytechnique, Ravier, Meteo France, have been very instrumental in these field campaigns. So these balloons are launched from the facilities of the National Science Foundation in Antarctica, okay, which is a very logistical adventure. So they are launched up. So they go inside the vortex. And the idea was to follow them. Now, the number of balloons is not overwhelming, as you can imagine, because each one of the balloons is very, very expensive. So we can manage to launch 27 in the first campaign, 2005, and 19 in the second, 2005. So they are called super pressure balloons because they become spherical, they don't change the shape, and so basically they rotate, they move around for 2 or 3 months on surfaces that are mostly of constant density. Okay? So the number of balloons is relatively small, but they are there for 2 or 3 months, so they can help us to look a little bit at motions. That's the position of the balloons. You can Google these campaigns, and there are nice animations of how this balloon move around. Okay, now 28 October 2005, the balloons were in the locations indicated in the left plot. On October 2010, so in the other campaign, there were less balloons. They were in the position on the right. Mind you that you cannot launch more than maybe a couple of balloons a day, given the conditions in Antarctica, and it takes a lot of work also to launch one of these balloons. Okay, so we have some evidence, some tracers in the form of balloons that are at the constant density. The constant density is not exactly the same as potential temperature, but it's not so far away either. So we can interpret the motion of each of these balloons as a parcel, as a fluid parcel. In a very broad sense, we can follow it. So what we have done is we have done a two-step approach. We have look at some of the usual tools of the Lagrangian analysis to see how parcels behave in a flow for which we know the velocity field from observational data. And then we say, okay, we find something interesting. We go and look for if there was a balloon around. And if there is a balloon around the location where something interesting happened, did the balloon behave as we would expect? Okay, that gives us a feeling for whether we are understanding or advancing a little bit of the theory. The data is available to everybody. It's given by these very big programs in the national centers, both in the US and Europe. And we also have the data from the balloon campaigns. These balloons have GPS and have transmitters, so we have the temperature, very frequently, and we know where they are. The methodology is based on the calculation of trajectories. And the trajectories are found by just solving the equation dx dt equal to the velocity. Okay, so with some fancy interpolations and some methodology to avoid the problems of the pole with the coordinates and so on and so forth. So given the velocity field, that is what we have from the data, we estimated trajectories, and now we have trajectories. Okay, so the first method, and I do not know if Oscar covered this yesterday. The first method, very traditional, is the so-called finite time Lyapunov exponents. Maybe it will help me to know if Oscar mentioned these things yesterday. Can you tell me? Hello? Did Oscar Fuentes yesterday in the lecture cover a little bit the Lyapunov exponents or not? Do you remember? No? Okay, so what these Lyapunov exponents are trying to do is they are trying to tell you how far parcels go away from each other in time. Okay, how to quantify the dispersion of fluid parcels. And for this calculation, it's kind of simple. One fixes a grid point here in red, then takes points in a cross, right? Points to the right and to the left and up and down, okay? In the latitude and longitude, for example. One follows the trajectories, and in the x direction, then these go to the distance changes now in the x direction. In the y direction, the distance also changes. So one computes a matrix like this, dividing by the delta x divided by the distance that they have initially, and so on and so forth. And then one computes the eigenvalues of this matrix for each point. One takes the square root, takes the logarithm of that, and divides by tau, and this gives you value that is the Lyapunov exponent. And the exponent is as I said, it gives you a feeling for the dispersion of the balloons. And one gets a rather messy map, okay? Rather messy map. Because one gets now a maps of values. One gets a maps like this. And the important thing of looking at maps like this is look at the ridges of the Lyapunov exponents. And by the way, one can do this exercise with the particles going forward in time or backwards in time, and the interpretation is a little bit different. And that's already a challenge, because one wants to plot ridges. And imagine you are plotting with a contour plot. You are plotting the mountains. Of course, when we are plotting the Andes, the Andes will appear as a very big mountain with contours of topography, right? But if we want to plot the very top of the mountain using a contour subroutine, it's very difficult, because the top of the mountain is just a line, okay? But so all of these things are approximated. And what it basically tells us is that, and not so colorful, is the type of thing that I just put on the screen. This is the more working version of these Lyapunov exponents. These are values. And then the idea is that parcels will go away from some of the lines with a certain color. Let's say they go away from the parcels that the lines that are computed in red. Okay, or they get close to the parcels that are painted, the lines, that are painted in blue. So one gets a feeling of how the flow is organized this way. But looking at the figure in the lower right, okay, it's not surprising, isn't it? I mean, it's not surprising that the flow, it looks like the vortex. I mean, in a vortex going from west to east. I mean, in a cyclonic sense. So the parcels are actually moving that way. Now, here is a complicated figure, and this figure has a lot of detail, because working with these tools, one encounters a lot of details. What this picture shows is that we detected an event going from 21 November 2005 22 November 2005 and 25 November 2005, of two balloons. And for that one, the balloons are indicated by these yellow circles. So here is one of the balloons, and the other balloon is here following. Okay, so they are very close. So it looks as if they will behave very similarly, but they don't. I mean, as they come close to the, to that domain, to that region where this tongue is coming out, one of them decides to escape to the left, and it goes along the tongue, and the other decides to stay inside the vortex. Okay? So, let me stop a little bit and talk about this type of ideas of the unstable and stable manifolds in a system. Okay, so let's say that we have a line, and this line acts as a repelling material line. Okay, we'll call this line an unstable manifold, and the red line is the line that we call an unstable manifold. So take a parcel, say, in the position P of T, or another parcel in the position P prime of T, and then see how they behave. And so they behave like this. Okay, they go along the very close along the blue line, and then when they get to the red line, they goes away. Okay, so they go away. So the blue line acts as a repelling line, and the same for the other parcel that was in the other direction. The intersection between these two lines is called a hyperbolic point. Okay. So this is the same story, but with the trajectories going backwards, okay? Which is going backwards in time. Now, the things are easy if all of these phenomena would be happening in a steady state or an autonomous system. Because when we look at, if we have evidence that in the flow, we have a structure like this, with lines crossing like this, crossings like this, we know the behavior of the parcels. Okay, we know the behavior, we know how the parcels are going to behave. But unfortunately, at this point, these hyperbolic points are moving around too. So it's very difficult to get a feeling for how the flow behaves. So jumping a little bit, because I don't want to show this picture again, which is complicated, what has happened with these balloons is something like this. On 21 November, on the upper top, here are the two balloons. One is in blue, and the other one is in yellow. And they were more or less on the same line, on the same side of one of these lines. But the situation changed as we came to 22. On 22, we found that one of the balloons had actually overcome the other and escaped from the boundary that this red line was imposing to the parcel. But the other one, the blue one, remained on the same side. So this parcel, the yellow parcel or the yellow balloon over here now could go away, okay, could move away, whereas the other one had to remain inside the vortex. And that's what's happening here. They are moved. The blue one is still inside the vortex, while the yellow one is going outside the vortex. Okay, so that's the type of behavior that one gets from dynamical systems. I mean, well, we do not really explain, exactly what's happening, but we are trying to describe. We are trying to put some order in the flow. Now, one of the exciting things in the work with the people in Madrid has been that they have come up with a nice Lagrangian descriptor. It's a simple one. It's a very simple one. It basically measures the length of trajectories. Okay, so you fix a point in a space, and you measure the length of the trajectories that go through that point in some interval, during some interval, t sub 0 minus t and t sub 0 plus t, okay? So if the trajectory is very long, the velocities are very strong. If the trajectory is short, of course, the velocities are weak. But the important thing in looking at these plots of M is that you have to look at the gradients. So when you have strong gradients, then you can distinguish regions where the parcel the flow is moving very fast and where the parcels are moving slow. So they belong to different kinematic regimes. Right? And that is an impression, and there are several papers. There's one that just came that has a very nice description of these ideas, and it just came in Elsevier Science journal. Okay, so if we use that M, then we instead of potential vorticity or instead of any other the outcome of exponents, we get these kind of cute plots. Okay, and these cute plots, we see the evidence of the structures, like this structure that is pointed by the letter H here with a white. Okay, so this structure is something like this. Okay, we see this hyperbolic point now outside, in the location outside of the vortex has formed. So from the dynamical system perspective, again, when we look at the picture that way, we find an order. We find some order in the way that the parcels are moving. Okay, now this is outside of the vortex, and this is not a very new finding. Bernard Legras in Paris have demonstrated the existence of these points. But what we found was that these points were also present inside the vortex. Okay, so this is another one, and for that Alvaro had very incredibly patient in looking, as you can imagine, image by image. And so here is the point Q3, and if you enlarge the picture on the left around Q3, you see that picture on the right. Okay, and this looks certainly like a hyperbolic point. Okay, look at the division of different areas with different kinematic properties. Now, furthermore, we see the influence or the signature of these hyperbolic points in the tracers. The left-hand side is again M, computed based on trajectories, but the right-hand side is the ozone. Okay, so ozone is the green. Look at the green. I mean, so the green is the same, more or less the same concentrations of ozone, and look how the ozone has gone from the inside or near inside the wall of the vortex to the inside, okay, just to the inside of the vortex. So that tongue of ozone is evidence of the presence of a hyperbolic point that is associated with the flow that is consistent with this. Okay, so that was a finding, and that encouraged us to look into I'm going to be jumping a little bit because we are about 20 minutes now. And we're talking about the phenomenon called Rossby wave breaking, and can we use this type of a tool that is, we are confident now that by patience and inspection and good eye, by plotting this function M, we can detect the presence of these hyperbolic points. So can we use this to see the signature of actual waves that are breaking in the field, and the challenge is that all of this is highly transient in time, and it's very nonlinear, of course. And I'm going to jump over this, but jump by saying that in an autonomous system that is independent of time, things are very easy. But when things are a function of time, things are complicated. In the top frame, you see the famous cat-eye structure for a Rossby wave. So basically, a Rossby wave is a wave that has been propagating and has encountered a level where the wave has grown. And in that level where the wave has grown, these cat-eye structures have developed. Okay, these rotating in different directions. I mean, they have developed. Okay, and the air, if this is perfectly stationary, this is an autonomous system, then there is no air that will go through in and out of these cat-eyes. But if there is a transient, if the motions are dependent of time, then if the flow, the parcel can start crossing now, because the streamlines and the trajectories do not coincide anymore. So the parcel can start crossing. So this is a tracer. The bottom figure shows a tracer, and the dark color is a tracer that was put in the flow, and this tracer has gone up inside the cat-eye and is wrapping around the cat-eye. Okay, it's wrapping around the cat-eye. So our goal, our interest is, try to find these hyperbolic points and interpret them as cat-eyes and of waves, that are breaking. Now we have tried to do the more classical approach with potential vorticity as a tracer, and we have found that things are okay. And so that's kind of a nice looking view of these breaking waves that develop. All of this breaking and all of this tearing and all of this mixing in the stratosphere develops what people have been calling a surf zone. That is outside of the vortex. Okay, so this is basically our philosophy. Okay, we look for instantaneous stagnation points in the field, and we try to interpret them as hyperbolic points. Then we try to see whether we can find evidence of Rossby wave breaking, okay, of waves that have achieved a nonlinear stage and they break and they have generated these structures. These points, because the flow is non-stationary, they move around and they form hyperbolic trajectories. And looking at these hyperbolic trajectories, we try to gain insight on the structure of the flow, Okay? So here we go. Let's look at. We were wondering before. Remember, if we can find cases where the balloons the balloons themselves were inside the vortex, and we can see them going away from the vortex, from the inside, escaping, showing structures that they are very small and they cannot be seen by the analysis of the operational centers that have a very limited resolution. So here is we go back to 17 September of 2005, and over here, if you can see the southern tip of South America, even in the top of the Antarctic Peninsula, there is a green dot. There are actually 3 green dots that are superimposed on each other. These are 3 balloons that were in that location at practically the same time, almost touching each other. When we look at 15 October 2005, these 3 balloons, we follow them around, and they are here now. These are the 3 places where the balloon have been in 15 October 2005. So they have come from inside of the vortex, to the outside of the vortex. Now, how have they made it? What we have done is we have been plotting this function m, this Lagrangian descriptor of the function m, so obtaining maps like the one in the left. Now this map in the left is we have to enlarge it. Okay, so we enlarge it, and this big enlargement is the map on the right. Now, when we look at the map on the right, you see two features that I have to enhance them so we can actually appreciate them. Look at the, if you fix your attention in the, I guess that the, okay, it comes here L1, okay, in L1, that tongue, it has a slightly different color, has a different color, and colors and gradients are very important in the interpretation of M, okay? So that has a lighter color than the surroundings, and suggests that this part, the part that is inside L1, is linked to the yellow part that is to the above it, okay, above the L1. So it looks like that there is a continuity like this. And air, this air has actually come this way and mixed with the others. And this, the technical name for these features is lobes. Lobes. So you can see that there is a lobe that has been formed by the internal motion of the flow that has connected the inside of the vortex to the vortex itself, that is a red part where the velocities are very strong. Okay, so further analysis looks at, and looking at the evolution, we can see again another tongue or lobe that is now L2. And this L2 now is now linked to the air that is in the periphery of the vortex, or in the red part, that is here on the outside. Okay, just recall the position of the circle that we are trying to visualize. So what has happened is that if a balloon was in this location, in the location of yellow over here, it suddenly was taken inside the lobe and it moved too close to the vortex itself. And in there he found that another lobe was developed, and this lobe was connecting the location with the outside of the vortex. So in that way, the balloon goes from the inside to the outside of the vortex. This is an interpretation. It's based on lobe theory. It has gone to the reviewers. We believe that there is enough evidence in this highly turbulent flow for these kind of events. Okay, this is a summary of what we have seen, the Lagrangian vision of the stratospheric flow. The lines, the dark lines that we see around, they are a vortex, and they are all very nice and smooth. But in reality, the vortex produces filaments, there are lobes inside, and there are lobes outside, and these are manifolds that are coming from the flanks of the jet, or there are manifolds that are coming from the inside of the jet. And when the parcels get, or the ozone, for that matter, gets into these lobes, then they move it towards the inside of the vortex, or they go toward the outside of the vortex. And in some cases, the lobes that are inside, they connect to the lobes that are from the outside, and in that way the parcels will go through. The episodes are rare. Nevertheless, there is not a constant leaking of air parcels from the inside of the vortex to the outside, or from the outside to the inside. But I believe that that gives us a feeling of how a Lagrangian vision of the flow. I'm not going to talk about the ocean. It was too ambitious of me to mention, and I'm sorry about misleading. I'm not going to be talking about the ocean in this talk. The author, Mancho, has written several papers on the application of M to understand the behavior of ocean eddies, the behavior of the flow in the ocean eddies. I have a big concern, nevertheless, with the applications of these techniques to both the stratosphere and the ocean, to be frank, and is that the paradigm is based on two-dimensional flows. Okay, we are even though in the atmosphere here we have been working on potential temperature constant surfaces. And we know that the parcel has to maintain the potential temperature, so it's approximately right. However, when there are very strong deformations in a fluid, then there are vertical velocities that are associated. Okay, there are fronts that form in the fluid, and there are three-dimensional motions that are very crucial. And recently, for the ocean, it has been shown that the so-called sub-mesoscale eddies then also generate important vertical velocity fields. So how much of the vertical velocity is challenging this type of two-dimensional picture that we are trying to put together? Okay, is something that to be looked at in the future. Nevertheless, we believe that I would like to transmit the question we had. The question we had was to use tools of dynamical systems to give insight onto the wave dynamics. It's easy to say that one can generate waves by instability processes, but we wanted to see evidence of these waves. In the stratosphere, people have done Fourier decompositions, and they look at Fourier components. But believe me, the Fourier components you never see the Fourier components in the real world. I mean, the real world is too complicated for that. So you can see the superposition of these, but when you look at Fourier components and you start thinking about critical layers and things of that sort, very, very difficult to associate critical layers unless you work in a very simplified model, which is very, very good, nice for learning, but very, very difficult to apply. Okay, so in the future we plan, why not, to look at some in more detail at some other years. I mean, we don't have more balloons for other years. Maybe there will be another balloon campaign, but it will be in the tropics. But we have looked at the reanalysis only for some times, some of the years in detail, and not always at all times. And also we plan to look at the Northern Hemisphere. In the Northern Hemisphere, the vortex is more tortured. I mean, the vortex becomes extraordinarily distorted by waves, especially in summer, in winter. So it will be a big challenge to see whether we can apply these tools or these ideas to explain how the air and the ozone air, with rich air, goes into the pole in the Northern Hemisphere. So, thank you very much for your attention to this. Any questions?
Okay, so thank you, Roberto, for this.